Hello students, we'll be looking at the halogen derivatives class exercise 1. It's a pretty straightforward class exercise. However, there are several things that are very fundamentals and they're very important for you to take note of, and that's why we deliberately craft certain questions in a certain ways so as to share with you that these are the important concepts you need to be aware of. So for example, for 1a, the question asks how would you expect the rates of the reaction to compare to that of the reaction of 2-iodo butane, and this is in comparison with 2-bromobutane. As you might be aware, the structure of 2-bromo looks something like this, and the structure of 2-iodo look something like this. So the only difference is in the C halogen bond. So one of them is CBr, the other one is Ci. If you take a look at the data booklets, you will realize that the CBr bond has a bond energy of about 280 kilojoules per mole, whereas that of Ci is about 240 kilojoules per mole. Okay, and of course, if you need to refer to some of the parts in the lecture notes which present the fundamentals, please feel free to do so. Yeah, but over here, I'm just going to summarize a very important idea that you need to be aware of. That is, for SN1 and SN2, yeah, so regardless of whether you're looking at SN1 or SN2, right, the breaking of the C halogen bond occurs in the rate determining step. How do you know that? Well, I mean, first of all, it's through experiments, and from the lecture notes, they present some of the very fundamental LOs that you need to be aware of. So for SN1, the rate determining step is rates is equals to rate constant multiplied by the substrate. In this case, is I just spell it out as a substrate to the power 1. So that's first order with respect to the substrate. Okay, so for SN2, it is rates is equals to K multiplied by substrate to the power 1 and multiplied by the nucleophile, again raised to the power 1. So it's overall second order. Yeah, so in both of these rate law, you notice that both of them contains the substrate as part of the rate equation. So that means that the breaking of the C halogen bond occurs in the rate determining step. Yeah, and because of that, the stronger the bond is, the more difficult it is to break, the slower the reaction. So the more difficult it is to break will correspond to a higher activation barrier. Okay, so let me repeat. The CBr bond is stronger than the Ci bond, so that means that the CBr bond is more difficult to break. Yeah, so because the CBr bond is more difficult to break, that means that in the rate determining step, when you transit into the transition state, yeah, because the reaction occurs via the activation, the energy profile diagram that looks something like this. So if this is energy and this is the profile of reaction, or you can call it the reaction coordinate. I think in tutorials I often call it the reaction coordinate because it's actually the more correct term. Yeah, so if I use the orange pen as SN2, sorry, so this is SN2, maybe I just zoom in. So this SN2, one step. So in this case, the transition state will look something like this. So in this case, the HO is the nucleophile, and then dot partial bond formation, and then the C is in the middle, and then dot. The X is partially being broken. Okay, so this is the transition state with an overall negative charge, and of course these are the rest of the groups, which in this case I don't want to draw them out. Yeah, so in this case, you notice that the breaking of the C halogen bond occurs, in the rate determining step, and that is part of the transition state. So the stronger it is, the more difficult it is to break. All right, then you might be asking, we didn't learn about SN1 transition state. How does it look like? Okay, so I'm just going to sketch a similar diagram. I'm just going to find some space here using green. Okay, so I have energy here. And then I'm just going to say this is the reaction coordinates. Okay, and then I'm going to use the same orange. Okay, so SN1 will look something like this. So first you need to break the C halogen bond. Okay, over here, and this is the intermediate, and then after that it will go through a reaction with a very low activation barrier through the carbocation. Okay, so in this case, if I'm going to predict how the transition state will look like, it will probably look something like this. Okay, so it will be more of like I have a bond here, I have a bond here, I have a bond here, and then the transition state is breaking apart. Okay, because the X is leaving. Okay, then this is the transition state with a negative charge. You'll notice that in this case, the transition state does not involve the nucleophile, right? Because remember that the rate determining step is over here. It's the first step, and later on we're going to draw the mechanism lah. So therefore, for the rate determining step, it only involves the breaking of the C halogen bond. It does not involve the nucleophile coming to form the bond with the electron deficient center. Okay, so I went a little bit in depth in the explanation, but I hope it's able to clear some doubts you might have lah. So regardless of whether it is SN1 or SN2, the breaking of the C halogen bond occurs in the rate determining step, and therefore, right, I would expect the stronger the bond is, the higher the activation barrier, the slower the reaction. Yeah, so in summary, over here, right, my answer would be I expect the rates of the reaction involving 2-iodobutane with sodium hydroxide to be faster, okay, than that's involving 2-bromobutanes. Yeah, I hope that is able to give you a more complete view of the answers to 1A. Alright, then next we're going to move on to part B. For part B, we were told that I have a pure sample of 1 enantiomer, so maybe just you decide which enantiomer you want to draw. It doesn't really matter here. Remember that for H2, because you did not learn how to name enantiomers, right? So in that sense, you can just draw any enantiomer you're comfortable with. Okay, over here it says that it's theorized to undergo 50% SN1 and 50% SN2. Yeah, so from here you can easily perform a calculation to decide whether you have more of one enantiomer over the other. Yeah, but I think that is the next question, so it's not so important at this stage. So over here, you have a very standard phrasing. You're supposed to draw both mechanisms, showing curly arrows, charges, dipoles, relevant pairs of electrons, relevant stereochemical orientation, including the 3-dimensional structure. Yeah, so it's really up to you how you want to show it. But remember that where appropriate, please ensure that you drew in the 3D wedges. Okay, meaning the hash and a wedge. Okay, so right now I'm just going to very quickly show you how they're going to look like. Okay, so I'll begin with SN2, because SN2 is the easiest to draw. Remember that for SN2, the rate determining step involved 2 species, the nucleophile and the substrate. Okay, so because these two, or rather 2-bromobutane, right? So I'm as what I've illustrated during the lecture series, right, the best way to draw it is to showcase a tetrahedral geometry like this, okay, because we want the nucleophile to approach from the left, okay, so that we can easily show stereochemical inversion in your examination scripts. Okay, so this is the best way to represent it. Okay, so delta plus, delta minus, and then I'm going to draw in the rest of the group, CH2, CH3, and then this is H, and then this is CH3. Okay, and then the nucleophile in this case is hydroxide anion. Remember to draw in the lone pairs. Okay, so what exactly are we marking for? We are looking for the dipoles, okay, and then the wedges, and then of course the lone pairs over here. Why is the lone pair important? Because in your arrows, right, you need to show that the electron source is the lone pair attacking the electron deficient carbon here, and then the CBr bond will break towards the bromine, which in this case is what we call the electron sink. Okay, and for some reason, Cambridge requires us to draw the transition state for SN2 in your examination scripts. So yep, so that's why we emphasize it in your lecture notes. So when you draw in the transition state, this is how it should look like. So I have a OH here, I dot that shows partial bond breaking, or rather in this case partial bond formation, and then dot partial bond breaking of Br, and then I draw in the rest of the groups in. Okay, so this is actually a trigonal bipyramidal kind of transition state. Yeah, but it is not a perfect trigonal bipyramidal because the bond will favor breaking in one direction over the other. But this is not the purpose of the H2 curriculum, so I will not go into details. And then the overall charge mass balance, remember to put a minus. Alright, some of you asked me in tutorials, you have seen somewhere that you need to write a double dagger here, so is it necessary? Alright, the double dagger actually means transition state. So if you don't feel like spelling out transition state, you can put a double dagger. But if you feel like spelling out transition state, you can just spell out here transition state. Okay, for me, I'll just write the double dagger, but it is not really too common in H2, so maybe you can choose to just spell out transition state. Yeah, but of course, for simplicity, as what I often share with the students, it's good to just put the double dagger in. Okay, and then of course I need to show the stereochemical inversion, so I put the HO over here, and then the carbon, and then CH2 CH3, and then project in H, and then project in CH3 plus Br minus. Okay, so what are we looking out for? Most students will actually forget to balance the equation. So remember that conservation of mass is important here. So the Br minus is being expelled. So make sure you include that in. Okay, and most students might unknowingly cause the inversion not to take place. So they swap the H and the CH3. So remember that this is a fatal error. Yeah, you shouldn't be swapping the H and the CH3. Yeah, if it's projecting inwards here, it should be projecting inwards here. How does the inversion takes place? It is the nature of the reaction, because if this is a cone like this, then after the reaction, you sort of turn the cone inside out in this fashion. Yeah, if you can imagine it, good. If not, then I think you can just take it to be the facts lah. And some of the students also asked me what exactly is the meaning of stereochemical inversion, and I thought maybe I can clarify a little bit over here so that perhaps it's clearer to those of you in doubt lah. Okay, so it is called a stereochemical inversion because if you take a look at maybe I'll just circle this part. This, if I rotate it 90 degrees, it looks something like this. Okay, so Br carbon, okay, then CH2 CH3, and then project in and then project out, which is the CH3, right? Yeah, then if I turn this 90 degrees, right, it will look like this. OH, oh sorry, I just superimpose them together. Okay, OH and then carbon, right? And then you notice that CH2 CH3 is over here, project in H, and then project in CH3, right? Yeah, so can you try to imagine, although this is not perfectly correct to say that, if I draw a mirror plane here, right, and if these two groups are the same, these two are actually mirror image some sort. So that means that in the course of reaction, right, if let's say we are maintaining the same nucleophile Br minus, right, it will lead to racemization. Yeah, so the reason for the racemization is due to what? A phenomenon called stereochemical inversion. Yeah, and that is the reason why in SN2 we wrote it in the notes that it results in what we call stereochemical inversion or inversion of stereochemistry. That is a short way I can use to explain to you. I think the details are actually in the lecture video, so if you wish to, you can watch it again. Right, the next mechanism we're going to draw is SN1. Okay, so I need to label SN2 here so that it's not confusing. Okay, so for SN1, right, again SN1 is pretty straightforward. We can show a flat structure first. It doesn't really matter. So Br delta plus delta minus. So again, the C-Br bond breaks towards the Br, and this is actually the slow step. And you might have seen in the lecture notes that this is actually an equilibrium reaction. So if you wish to be a little bit more accurate, you can show equilibrium here. Then you actually generate a carbocation, okay, plus Br minus. Okay, and then up to this stage, you do not really need to show stereochemical, or rather stereochemistry. Yeah, because you can show it in the fast step. Yeah, so if then from here onwards is what you have learned in electrophilic addition, the chapter on alkenes lah. So I can show the stereochemical projection of the carbocation over here. So I can have a H here projecting inwards, carbon, and then I can have a CH3 here projecting towards you, and then a CH2 CH3. Okay, so this is a carbocation. Then I'm just going to show you that the nucleophile here can approach from the top face of the carbocation, and the nucleophile can also approach from the bottom face of the carbocation. Okay, if we approach from the top face, we're going to end up something like this: nucleophile on top, bonded to the carbon, and then we're just going to push this downwards. So push this downwards like this. Okay, then I'm going to get a CH2, CH3, and then projecting in, and then a methyl group projecting towards you. And if you approach from the bottom, I run out of bit of space, so I'm just going to put here carbon. Okay, and then the CH2, CH3 is still here, and then H projecting to away from you, and then the methyl group projecting towards you. And then if I draw a mirror plane, they are direct mirror image. I forgot to put CH2, CH3. Okay, so this CH2, CH3. Yep. Okay, so SN1 will give you a racemic mixture, because the probability of the nucleophile approaching from the top and bottom plane, the probability is about the same. So we say that it approach top and bottom plane with near equal probability. Yeah. Why do I use the word near equal? Because it's not always the same. If there is a chiral center in one of the groups, for example, if there's a chiral center here, here, or here, right, then you will get not a 50-50 mixture, but you will get one higher than the other. As to the exact reasoning, I think I will save it for future videos. Okay, and then of course for part C, the question asks you to deduce the optical activity and purity of the final enantiomeric mixture of butane-2O, assuming complete reaction. Okay, so over here, right, you were told that you get 50-50, right? Right. Okay, so let's say we give the structure a name. So for example, for this particular molecule, right? Let's say this particular molecule, I call it A. Okay, I call it enantiomer A. Okay, this enantiomer A. Then if I look at these two, right, which one is actually A? So this is actually A. Okay, and then this is B. Alright, so we started off with pure enantiomer of 2-bromobutane. So if it undergoes 50% of SN2, so let's say 50% of SN2, right? So I'm going to get, so let's say I split the products into 4 parts. Okay, so I split the product into 4 parts. Then I think it's easier to explain. Okay, right, into 4 parts. Then 50% of it undergoes SN2. So therefore, right, all these, okay, these are actually A, which is produced from SN2. Right, because 50% of it undergoes SN2, which is what we agree on. Okay, and then out of the 50% that undergoes SN1, I get 50% of A. Okay, so that means that from SN1, this is from SN1, so this is also A. Okay, but this is from SN1, and then the other portion, which is here, yeah, so this is B. Yeah, so this is also from SN1. Yeah, so in this case, I'm going to get 75% of enantiomer A. Okay, so all in all, I'm going to get 75% of A and 25% of B. Yeah, by virtue of a simple calculation that I have demonstrated in the bar chart above. Okay, so for part C, you can explain in any way you want, as long as you are able to highlight that 50% of the pure enantiomer of one form, in this case I call it A, comes from SN2, and then the remaining 50%, right, half of it will also result in A, because SN1 gives you equal probability of both products. Okay, both enantiomers. Yeah. Alright, so next we're going to move on to question 2, which of course is an MCQ. Hopefully it's a little bit more straightforward. So you were told that you have this compound known as 1-bromo cyclohexene. It's unreactive towards nucleophile. That means that it is resistant to nucleophilic substitution. This is not too much information, because you are aware that for halogens bonded to sp2 hybridized carbon, they are resistant to nucleophilic substitution. What did you learn? You learned that they have partial double bond character. Okay, so if I'm going to sketch out just a flat version of the cyclohexene. Of course, you know that it is not true, but I'm just going to sketch out a flat version of this particular structure, right? I'm going to have the pi system in grid, so that's 1 electrons each, right? So this is like the pi bond between the 2 carbon, and then I'm going to represent my bromine in purple or maroon, and then this bromine, right, is actually in period 4, so it will have a much bigger p orbital, much larger p orbital. Although the 2p 4p pi overlap, right, is poor, but better than nothing. So that is because they have pi symmetry. In higher level chemistry, we say that the bromine over here, right, has a lone pair of electrons in one of the p orbitals, what we call pi symmetry, and is able to overlap side on with the pi bond, resulting in the 2p pi overlap of the 2 carbon. Yeah, because they have pi symmetry, they can overlap side on. So we say that so what you learn in H2 is that you can highlight that the lone pairs of electrons will partially delocalize into the CC pi system. Okay, so I repeat, the lone pairs of electrons on bromine, right, will partially delocalize into the CC pi system, and the partial delocalization, right, will result in a partial double bond character, making it resistance to SN2 or even SN1. Yeah, it is resistance to SN2 because, number one, right, for SN2, the nucleophile must come from the rear. Okay, but you notice that the rear is kind of like blocked by this ring, and at the same time, when the nucleophile tries to approach, it will be repelled by the pi electron clouds. Okay, and of course, secondly, right, due to the partial double bond character, the C-Br bond is strengthened. So remember that the breaking of the C-halogen bond, regardless of SN1 or SN2, right, occurs in the rate determining step. So if the C-Br bond is strengthened, that means that the activation barrier is likely to be higher. So therefore, much slower reaction. Since the tail is unreactive, means in this case cannot react. What about SN1? SN1 is not possible because if it's going to undergo SN1, right, it will look something like this, very weird structure. So if it undergoes SN1, you still have the pi-pi overlap, but you're going to end up with a p orbital that looks like this with a plus charge, and it is not stabilized. Yeah, so this p orbital is not stabilized because it's orthogonal or perpendicular to the CC pi system. So because it's not stabilized, it is resistance to be formed, and that means that reluctance to be formed in that case. So it wouldn't want to be formed, and it will rather not break. Yeah, so that is the reason why 1-bromo cyclohexene is resistance to attack by nucleophile. Yeah, but for 3-bromo, very easy to attack because it's a normal sp3 CBr bond. SN2 is possible, SN1 is also possible. In fact, SN1 is even more possible because the positive charge can delocalize into the CC pi system. So I'm going to just illustrate it here for our complete understanding. So if this is the CC pi bond originally present, okay, and let's say this is the Br, right, and let's say it breaks like this, right, okay, after it breaks, right, it's going to have an empty p orbital over here, and then this can actually partially overlap with the CC pi system, therefore reduces the positive charge of the carbocationic center. Yeah, so it is even more reactive towards nucleophilic substitution as compared to a normal halogenal alkane. Yeah, okay, so with this background, let us try to take the option. So what could be a reason for the lack of reactivity? So our focus is lack of reactivity of 1-bromo. So let's focus on that. Electron of the pi, or the electrons on the bromine atom delocalize in the pi bond. Okay, so that explains. I've already explained earlier on. Electrons of the pi bond repel the attacking nucleophile. Yep, that makes perfect sense as well. And then the presence of the pi bond prevents free rotation. Again, this has no bearing, right? It is true that there might not be free rotation, but it doesn't explain why it's unreactive towards nucleophile. Yeah, so because of that, we are not going to choose option 3. We're going to choose options 1 and 2. Okay, so we are done with halogen derivatives class exercise 1. We're going to move on next to halogen derivatives class exercise 2 in the next video.